Hello and welcome to this video on chemistry revision for the 2022 exams. In this video we're going to be covering everything from the first topic, atomic structure, and the periodic table. Please subscribe if you find these helpful so that other people can find them easier. And before we start, I just have two things to talk about quickly. First of all, chemistry, especially chemistry paper 1. It's probably the trickiest science because you don't just have to know loads of facts, you have to be able to understand how different atoms and everything work together and react together, and then apply them to things that you won't have studied before. And that's why I think this is the trickiest topic. And also, it's going to be a bit different to the other two videos I've made on biology, because those PowerPoints take way too long to make, and I want to get through the entirety of biology, chemistry, and physics. So what I've done for this video is I've simply made lists of questions instead, and we're going to talk through them. So without further ado, we're going to head on over to the advanced information. So the advanced information for chemistry is not exactly the most helpful because nothing has been taken out completely, so you need to know everything still. But you do have a major focus, and in this video we're doing all the 5.1 stuff. So for Combined Science Foundation, you need to focus on the periodic table stuff. For Combined Science Higher, neither part will be a major focus, but you still need to know it as there will be questions on it because nothing's been taken out completely. For chemistry as a single science, or triple science as I'm going to call it throughout the video, both topics that we're covering today, they're both coming up. I should note we're not actually covering any required practicals in this topic because there aren't any. And for triple science higher, the periodic table is going to be your major focus, but once again you still need to know stuff from the basics. So we're going to start by having a look at some of the very basics of chemistry. So pause the video and have a go at these, and then we will go through them. So an atom is simply the smallest possible unit of an element. That's the definition. The definition of an element is it's simply like a substance made up of atoms, all with the same number of protons in their nuclei. So each element is composed of atoms with a unique number of protons in their nuclei. So hydrogen has 1 proton in its nucleus, helium has 2, lithium has 3, and that's how the periodic table is made up and ordered. That's the atomic number, which we'll come on to later. A compound is a combination of 2 or more elements which are chemically bonded together. That's very key, chemically bonded for compounds. Reactants are simply 2 substances, whether they be elements or compounds, that react together or can react together, and the products of a chemical reaction are simply the things that come out, the results, the end products. Here is the basic symbol equation for photosynthesis. To do the word equation, you'd just replace these with words. Remember the arrow instead of the equals. I'm not going to go through the very basics, but it's so important that you write the 2's down at the bottom in subscripts and not as big. The big numbers go before, and those are how we balance. They represent the moles. These represent the fact that there are 2 oxygens bonded together here, as well as the carbon. And don't write a little o either, write big O. For the word equation, you'd simply write carbon dioxide, water, glucose, this is glucose, and oxygen. And if you can't remember this, you're going to have to revise it for biology. So what we do to balance it is we simply count up the amount of atoms on each side. So we have 1 carbon over here, we have 3 oxygens, and we have 2 hydrogens. And on this side we have 6 carbons, we have 12 hydrogens, and we have 8 oxygens. So what we're going to do is we need to get them all the same. So how do we get from 1 to 6? We times it by 6. So we're going to put a 6 in front of here. So now we have 6 carbons. The carbons are balanced, but this has also affected the oxygen. So now we have 12 oxygen here plus another one here, which makes 13 oxygen. So we're going to look at balancing the hydrogen next. So we've got 12 on this side, 2 on this side. We need to times the hydrogens by 6. So we're going to put a 6 here. 6H2, that's going to be 12. And now our hydrogens are balanced. But remember, this again has an effect on the oxygen. So while we got 12 here, we've now got another 6 here, which makes 18. So now we need to get from this 8 to 18 over here. Remember, always go from smaller to bigger because you add numbers to the smaller ones. So what can we do to this side? Well, we got an 0.6, and this quantity is with the big one, so it isn't really going to change. So we can kind of subtract 0.6 off of this, so which makes 12. We need to make 12 oxygens from our O2. How are we going to do that? By adding another 6. So 6 O2 makes 12, and then add the 6 we took off makes 18. So we have 18 oxygens on both sides. A good way of remembering how to balance the photosynthesis equation my teacher taught me is it's the devil's equation, because we got 6, 6, 6. And then glucose is just, you just got to learn glucose. Question 6 asked you to find the 16th element's name and symbol. So we go along, 16th element is sulfur. Remember, we're looking on the bottom. We'll come on to atomic number and mass number later. But this atomic number, proton number, it's also called, this is the number of protons. As I mentioned, hydrogen has 1, helium has 2, lithium has 3, etc. Sulfur is our 16th element because it has 16 protons, and the symbol for sulfur is S. This is the atomic symbol, as it's called. So why I was telling you to write C and a big O in the last equation to show carbon dioxide is because C with a little o would be cobalt. So we're going to have a look at mixtures now, and a mixture is simply a jumbled up combination of elements and compounds, but they aren't chemically bonded and their physical properties don't change when they're in the mixture. So a solute is simply a dissolved solid in a solution. A solvent is the liquid that the solid is dissolved into. A soluble substance simply means it can dissolve. Insoluble means it can't dissolve. And a solution is simply the mixture of the solvent and the solute. So now we're going to look at the separating techniques. So the difference between separating substance using evaporation versus using crystallization is evaporation is simply where you put a solution in a Bunsen burner, you evaporate off the solvent and you're left with the solute. So you may do this with seawater. The water evaporates, the salt's left behind. Crystallization is a bit different because you evaporate some of it, but then when you see some of that salt crystals starting to form, you stop you stop heating it using the Bunsen burner, you take it off and you leave it to cool over a few days or however long, and that then the salt will become insoluble in the cold, highly concentrated environment, and you can drain off the excess solvent and you can have your crystals. The reason we use crystallization, because it would be easier to always use evaporation, is because some salts decompose when exposed to heat. So that's when we would use crystallization, separating a soluble salt from a solution. We have to do that in a practical later. How do you carry out paper chromatography? So if you remember, we take our bit of paper, we draw a line in pencil across it because pencil is insoluble, and we place it into a glass beaker with our solvent in the bottom, usually water but sometimes ethanol, and before we do that actually we put the dots of ink on it, don't we? And then we stick it in the water and the inks all rise up and the little dots separate out, and we go into this in more detail in paper 2. But basically what's happening is as the dyes from the inks move up the page, they are moving between the solvent that's moving up and the paper. So we call the paper the stationary phase, and we call the solvent the mobile phase, and the parts of the mixture that spend the most time in the mobile phase, they move further up the paper before they stop. Filtration first. That's the simplest one of the lot. You take a filter funnel, put it into a glass beaker. You take some filter paper, it's the sphere, you fold it into a quarter, you pull it out so it's in like a cone shape, and you put that into your funnel. Then you pour your mixture of a liquid and an insoluble solid. It's important. Filtration can't filter soluble solids, and you allow it all to drain. The liquid will fill the glass beaker, and the soluble solid remains in the funnel. Simple distillation is, well, as the name suggests, it's more simple than fractional distillation. So you simply have two liquids, or a liquid and a solid, in a flask. You bung the top and attach the top of the bung to a condenser, so it's simply just a tube with water, cold water around it. So then you can heat this flask, put it over a Bunsen burner using a tripod and gauze, and then as the liquid with the lower boiling point of the two liquids you have in there evaporates, it will go up and into the condenser, where it will cool back into a liquid, and you can put a glass beaker to catch that liquid, and then you've separated them. Fractional distillation is different. You have a mixture with lots and lots of different liquids in it, and you're going to take a fractionating column. Again, we look at this more in detail in paper 2. So you'd heat the liquid at the bottom of the fractionating column. It would rise. The liquid with the lowest boiling points will rise to the top, and they, because of how a fractionating column is laid out, they will be caught by the highest bit and go through the highest condenser, and then next highest, and as you go down, their boiling point increases until the liquid with the highest boiling point, it will barely make it up, because as the liquid evaporates and travels up as gas, it cools. Here's 15 more questions on the next topics that we need to cover, so pause and have a go if you want. So a mixture of sand and water, that's an insoluble solid in a solution, which means we're going to use filtration. A felt tip pen contains many solutes. The dyes are solutes, so to separate many different solutes from a solution we use paper chromatography. Crude oil is a mixture of many different liquids with different boiling points, so we're going to separate it using fractional distillation. To separate salt water, if you wanted the water, you could use simple distillation, because you'd be able to collect the water through that condenser. But if you wanted the salt, you could use simple evaporation or crystallization if you knew specifically that the salt decomposed under heat. The key here, when you're given an example of, you're asked to name a separating technique, is you need to remember that crystallization is used to separate a soluble salt from its solution. Paper chromatography is used to separate lots of solutes from a solution. Filtration is used to separate an insoluble solid from a solution. And simple distillation is used to separate two liquids with different boiling points, or in this case a liquid and a solid if you want the liquid. And fractional distillation separates many different liquids with different boiling points. A proton has a positive charge of +1, neutrons are neutral, so 0, and electrons counteract the protons, so they're -1. An atom's atomic and mass numbers, we looked at these briefly when we looked at the periodic table. The atomic number, the proton number, the number of protons in the atom, it's unique for every element. The mass number, the number of protons plus the number of neutrons, because the neutrons are the only other subatomic particles in the atom with any mass. So that's the answer to question 10. The relative masses, we say protons and neutrons have a relative mass of 1, and electrons' relative mass is insignificant compared to protons and neutrons, so you say roughly 0. It isn't 0 exactly, it does have a mass, it's just really, really small. So how big are atoms and their nuclei? Atoms are 0.1 nanometers, so that's 10 to the minus 10 meters, and the nucleus of an atom is even smaller. we say 10 to the minus 14 meters. It's really, really small. Now, the specification says you need to use real-life examples to compare the size of atoms and their nuclei. Well, you can simply say that, you imagine a pinhead, 5 million hydrogen atoms could fit in that tiny pinhead. That's how small they are. And nuclei, compared to atoms, they're really small. So you imagine if the nucleus is the size of a pea, the atom is the size of a football stadium. So it's just crazy to comprehend how small something can be compared to something so small, but there we go. And we've just done the relative masses. So isotopes are atoms of the same element, with the same number of protons, but a different number of neutrons. Isotopes have a different number of neutrons. And ions have a different number of electrons. So when we go on to talk about ionic bonding, that's when two atoms come together and form ions, because all atoms want to make a full outer electron shell of 8, which we're going to go on and look at, so we're going to talk about that in a bit. So to calculate the number of protons, neutrons and electrons in sodium using our periodic table, first of all, the number of protons is 11, because that's in reference to our atomic number, proton number. Remember, it's in brackets here. Proton number, number of protons. And the mass, this gives our total number of protons and neutrons, doesn't it? So 23 take away 11 is 12, because 11 protons plus 12 neutrons makes 23. So that's the relative mass, relative atomic mass of 23. And finally, the number of electrons is in a normal atom is going to be the same as the number of protons, so it's going to be 11. In an ion, because it's has more or less electrons, it's going to be different, and we'll look at that later. But in a normal atom, the number of protons and electrons are the same. Now, relative atomic mass and the mass number are not entirely exactly the same. So the mass number is simply the number of protons plus the number of neutrons. The relative atomic mass takes into account all the isotopes of an element. So we say that the relative atomic mass is the average mass of all the isotopes in an element. And I'm going to show you how we do this. So this was actually the 15th question. So we're given the fact that there are two stable isotopes of chlorine, 35Cl and 37Cl. So these are the mass numbers, 35Cl and 37Cl. Now, because we know that chlorine has 17 protons, then we know that this one will have 18 neutrons and this one is going to have 20 neutrons. So the relative atomic mass takes into account all the isotopes found of the element. So here's what we do to calculate it. We find how common each one is. So 75% of 35Cl. So what we do here is we use the percentage as decimal multiplier, so 0.75 multiplied by the mass number 35, and we add that because we want to make the whole number 100% by taking the average abundance of the two isotopes. So we're going to add that to 0.25 times the 37Cl, because that only comes up 25% of the time, and that comes out to 26.25 plus 9.25, which ends up coming out to 35.5. And this is why we see chlorine's relative atomic mass written as a decimal. You think, hang on a minute, we can't have half a neutron. No, this is the relative atomic mass because we're taking into account the abundance of the different isotopes of the elements. So here are 11 questions on electrons and the history of the atom. So pause and have a go. So electrons fill the lowest energy levels first. Now, energy levels are also known as electron shells, and you imagine them as the rings around the atom with the electrons on. The lowest energy level is the electron shell closest to the nucleus, the innermost, the one that can only have 2 electrons on it. And as you get out we say that the energy levels get higher. Sulfur has 16 protons, so we know a sulfur atom will have 16 electrons. Now I'm going to show you how to do this as a diagram, so you can have your S in the middle, or you don't have to have anything in the middle, but then you're going to do circles around it, and these are the electron shells, also known as energy levels, of course. You can call them either one in the exam, they'll accept it. And so the first one will fill up to a maximum of 2 electrons. So 2 electrons on the lowest energy level, and then on the next 2 there's 8. Remember, 2 on the first one, 8 on the next ones. So we're going to have 8 here. And 6 on the outer shell. Obviously I'm using crosses to represent the electrons, so we have 2 on the first shell, 8 because this is filled up completely, and 6 to make 16 because this hasn't fully filled up completely. How would you represent this using numbers? You would say that sulfur's electron arrangement is 2, 8, 6, because 2 on the first energy level, 8 on the second, 6 on the third. So, as we covered earlier, atoms react to get 8 electrons on their outer shell, or 2 if they're hydrogen. They want a full outer electron shell. That's their goal. That's how all atoms react, and that's the key to chemistry, essentially. So now we're going to move on to history. So before electrons were discovered, people simply believed atoms were solid spheres that couldn't be divided. J.J. Thomson discovered electrons in 1897, and he came up with the plum pudding model. So this was basically saying that atoms are balls of positive charge, and there's these tiny particles, negative particles called electrons, stuck in it. And then Ernest Rutherford discovered that atoms have nuclei, and you need to know how he did it. He performed an experiment where he fired alpha particles at a 1 atom thick sheet of gold. According to the plum pudding model, he expected all of the alpha particles to go straight through, but some of them, a small percentage, got deflected, so he had to conclude that there was something in the centre of atoms, and he called this the nucleus. And then he developed this nuclear model of the atom, which said that in the middle of the atom there was a tiny positively charged nucleus, while he said there were a cloud of negative electrons surrounding it. Ernest Rutherford also suggested that the positively charged particles in the nucleus were protons. Well, he gave them that name anyway. So Ernest Rutherford also discovered protons. Niels Bohr worked on this nuclear model even further. He refined it and said that instead of clouds of electrons, as we have just covered, electrons are arranged in electron shells, a fixed distance from the nuclei. James Chadwick experimented further, and he discovered that there had to be neutral particles inside of the nuclei, and he called them neutrons. So James Chadwick discovered neutrons. So there's 2 main differences between the plum pudding model and the nuclear model. In the nuclear model, the positive charge is contained in that small point in the centre of the nucleus, whereas in the plum pudding model, this suggests that the positive charge is just kind of everywhere and there is no nucleus. And also, in the nuclear model, or the modern nuclear model, electrons are arranged in shells fixed distances from the nuclei, whereas in the plum pudding model, electrons are just spread out throughout the atom. Now we're moving on to the periodic table bit. So here's our first 17 periodic table questions. Pause and have a go. Early periodic tables were ordered by atomic weight, so scientists would weigh elements and calculate the weight of each atom and simply put them in that order. But this was slightly incorrect because it didn't take into account the physical and chemical properties of the atom. So some elements were in the wrong groups and they were just placed incorrectly, some of them. The father of the periodic table, or the modern periodic table, is Dmitry Mendeleev, and he changed the order two ways. What he did is he switched round some of the elements, even though the atomic weight of one might have been bigger than the other, he switched them round so that they fitted patterns of how they reacted. So each column had similar properties, and he also left gaps for undiscovered elements. Many discoveries proved him correct. The main one was isotopes, that they proved him correct to not put elements in order of atomic weight, because isotopes, as we saw with relative atomic mass, we saw that some elements can have different atoms with different numbers of neutrons and therefore different weights. Protons proved the elements were all in the right order, because obviously the modern periodic table is ordered by atomic number, proton number. Groups are the columns of the periodic table. Each column has a number of electrons. Group 1, column 1, has 1 electron in its outer shell. Group 2 has 2 electrons, and this gives them similar properties because they will react in similar ways. The periods of the periodic table are the rows of the periodic table, and as you go down a row in the periodic table, the elements on that row will have an extra electron shell. So, if you will, the first period only has 2 elements in it because there are only 2 electrons that fit in that innermost electron shell. Here we are back at our periodic table. We have the groups labelled, so this group 1, 2, 3, 4, 5, 6, 7, and group 8 is called group 0. Here we'll look at them in a bit, and these are the transition metals. How you tell the reactivity of an element. So remember, they react to get a full outer shell. So this means that, well, first of all, group 8 or group 0, they already have a full outer shell, and this means that they are not reactive at all. Group 7, which only needs to gain 1 electron to make 8 on its full outer shell, and group 1 needs to lose 1 electron to make 8 on its outer shell. So they are the most reactive, and you know, these ones in the middle are less reactive because they have more electrons to gain and lose. But this brings me on to electron shielding. The electrons are attracted to the protons because positive and negative attract. So the closer the outer electron is to the nucleus, the harder it is to lose. So lithium still reacts, but not as much as potassium, which has electron shells between its outer electron and the nuclei, and this is what electron shielding is. It's where there's another electron shell that weakens the electrostatic forces of attraction between the negatively charged electron and the positively charged nucleus. So therefore, going down the periodic table here in group 1 produces more reactive elements. So francium is the most reactive element because it's got that 1 electron and it's so easily lost. In chemistry, we define a metal as an element that reacts to form a positive ion, whereas a non-metal reacts to form a negative ion, or it does covalent bonding and shares and it doesn't form an ion at all. So where are metals and non-metals? Metals are to the left, because if you think about it, these group 1 and 2, they're going to lose their 1 or 2 electrons, and because they're losing negative charge, they're going to become positively charged ions. You have a line going diagonally down here which kind of separates the metals from the non-metals, and in here you kind of have the semi-metals. You know, group 4, it can lose 4 or gain 4 electrons, but generally, especially carbon, it does covalent bonding, which we'll come on to in a minute, where they just share electrons, they don't lose or gain. But over here we have, like fluorine, the group 7, they gain an electron, which means that they become negatively charged. So these ones are non-metals: carbon, nitrogen, oxygen, phosphorus, sulfur, you know, arsenic, selenium, these ones, and the noble gases group 8 down here, these 0, these are the non-metals. So the important chemical property of a metal and a non-metal is its definition. So the chemical property of a metal is it forms a positive ion, chemical property of a non-metal is it forms a negative ion when it reacts, or it doesn't do ionic bonding, it can do covalent bonding. Non-metals don't form positive ions. That's generally a better way of putting it, whereas metals form positive ions. But the physical properties of metals, obviously, well, you imagine a metal, you know, it's shiny, they conduct electricity, conducts heat as well. It has high melting points, which means they're usually solids. You know, you don't really get metals as a gas, do you? They're solids. They're also quite dense, you know, they're tightly packed into that ionic structure, which again we'll look at later. Physical properties of non-metals, they can be different, you know, they have a lower melting point. We often find them as gases. They aren't great at conducting electricity and heat. You often see them used as insulators. They tend to have a lower density as well. So we're going to look at some of the groups in detail now. Suppose I have a go at these 12. The noble gases are inert because they have the full outer electron shell already that all the atoms are trying to react and get, so they don't need to react. Inert means unreactive. That's very important. Boiling point increases down the group because as the electrons increase as you go down the group, obviously because there's more electron shells, you know, you have greater forces between the atoms as there's more electrons, and we call them intermolecular forces, and therefore they're harder to pull apart and form gases. So that's why the boiling point increases as you go down the group. Properties, you know, they're unreactive, they're not flammable, therefore they're monatomic because they don't travel around in pairs, they travel around on their own. Some atoms, like oxygen, we always say O2 because oxygen travels around in pairs, it's diatomic, but group 0, noble gas, is monatomic. Now we're going to move on to group 1. Group 1 elements are very reactive because they have that one electron we talked about. They want to lose it, they can lose it very easily, and as we said, reactivity increases as you go down because the electrostatic forces of attraction between the outer electron and the nucleus grow weaker as the electron goes further away. That's known as electron shielding. Group 1 is also called the alkali metals. Group 1 reacts with non-metals, generally group 7, because they can give their one electron to the group 7, which needs one electron to form that outer shell. They generally form ionic compounds, you know, white solids that dissolve in water. We'll come on to the properties of ionic compounds again in the next video on bonding. That's another key thing in chemistry. Group 1 elements, very reactive. Their boiling melting points kind of, you know, in the middle. It's not low because you find them as solids, but it's not high compared to the transition metals. You know, it's around 100. Some of their melting points. It's kind of in the middle. Boiling point decreases this time as you go down the group, and relative atomic mass obviously increases because you have more of each subatomic particle as you go down. That's the same for every group. So the reaction with oxygen at room temperature, lithium, sodium and potassium, the first 3 group 1 metals, they react with oxygen to form metal oxides, which is why they're shiny, but then when you leave them out in oxygen they react with it, they go dull, they tarnish, we say, because there's that outer layer of dull metal oxide. It's different when you burn lithium, sodium and potassium. You're essentially reacting them with oxygen, oxidizing them. That's a combustion reaction. So what happens, and you need to know these for paper 2, so they're worth learning now as well. Lithium will burn with a crimson flame, sodium burns with a yellow-orange flame, and potassium burns with a lilac flame. You may well have seen how they react with water in class. They react very vigorously. So lithium, probably least vigorous, as we say, reactivity increases going down the group. So lithium, it kind of fizzes, it slowly shrinks, dissolves as it reacts with water when you put it in water. Sodium will fizz more violently, and it will rapidly disappear when it reacts water. And potassium, potassium burns. Potassium will burn with a lilac flame and fizz out, disappear quickly. With chlorine, they react to form metal chloride salts, so lithium chloride, sodium chloride, potassium chloride. Lithium reacts least vigorously, potassium reacts most vigorously. So our final 13 questions, we're at the end of the topic now, concerning Group 7 and the transition metals. These two I've put in blue because they are triple science only. If you're doing combined science, don't bother answering them because they won't be coming up. So pause the video, have a go. Group 7 elements are fairly reactive because they are trying to only gain one electron. They only need one electron, so as soon as they find that electron, they're going to react vigorously and try and get it. Reactivity decreases as you go down Group 7 because the electrostatic forces weaken as you get further out due to electron shielding, so that pull, trying to pull that electron over is weaker. So fluorine, the top gas in Group 7, is the most reactive. Group 7 are also called the halogens. Remember that, Group 7 halogens, the same thing. The first four elements of Group 7, you have fluorine, that's a kind of yellowy gas, chlorine, which is a kind of greeny gas, bromine is one of the few elements that's liquid at room temperature, it's kind of a browny, reddy kind of colour, and iodine is a grey solid. Relative molecular mass increases, as we said. Boiling point increases as we go down Group 7, remember that. We'd refer to it as relative molecular mass because Group 7 is diatomic. That's very important. We said that Group 0 is monatomic, Group 7 is diatomic, so they go around in pairs, covalently bonded pairs, so that they have the full outer electron shell. Group 7 bonds with non-metals to form simple molecular structures. They bond covalently. As I said, chlorine, for example, two chlorine atoms bonded together covalently. That's how they go around. They go around in pairs again. Group 7 also will bond with metals through ionic bonding. Group 7 will form negative ion. The metal that they've reacted with will form a positive ion, and they will form an ionic compound together. Chlorine plus potassium iodide, a displacement reaction takes place because chlorine is more reactive. So chlorine comes along, says, no, I'm more reactive, and it kicks away the iodine. So the products are potassium chloride and iodine on its own because iodine is less reactive. So that's what happens. Less reactive halogens get displaced by more reactive halogens. Group 1 are the metals, Group 0 and Group 7 are non-metals, and transition metals, as I'm sure you can see, they're the big block in the periodic table between Groups 2 and 3. Finally, this little triple science only bit, the transition metals. We have to compare the transition metals to the alkali metals. So transition metals have a much higher melting point. Remember, they have the properties of your generic metal. If you think of a metal, it'll probably be a transition metal. So it's denser, it's stronger, it's harder, with a higher melting point. It's also less reactive. Remember, Group 1 are more reactive because they only have one electron to lose. The transition metals have more than one. So with oxygen, transition metals react a lot less vigorously. They may not react at all. For example, iron slowly rusts in the presence of oxygen, whereas lithium, kind of that metal oxide layer on the top, forms very quickly. Water, transition metals will react slowly or not at all with it. And with halogens, again, transition metals will react more slowly or not at all. So this final question on the unique properties of transition metals. First of all, transition metals can form more than one ion because they have a variable amount of electrons. So for example, iron can form Fe2 plus and Fe3 plus depending on whether it's losing 2 or 3 electrons. Secondly, transition metals can form different coloured compounds. For example, iron 2 reacts to form iron 2 oxide, which is black, whereas iron 3 oxide is dark red. And finally, transition metals often make good catalysts, and as we covered, they're just things that speed up the chemical reactions. So, for example, iron is used in the Haber process, which again we look at in paper 2. So these questions on these 3 slides are basically all you need to know for your first chemistry topic. I hope that my explanations were clear enough. If you need anything cleared up, then go to the comments section and ask, and I'll give you a better explanation. Please subscribe so that other people can find the video more easily, and I hope this was helpful.